I invite all our speakers who are on the call to join the panel, and we can maybe brainstorm some of the ideas for future work and maybe research as well to tackle these kind of issues. And I guess to motivate the discussion, I would like to just ask you about your thoughts on, like, how do you think, like, what do you think the biggest opportunities are in terms of future performance work? Like, is it in the domain? Is it in specific technologies or hardware, or a mix of both? Anyone?
Sorry, yeah. So for your question, is that in what sense, in terms of performance? Like, can you kind of elaborate a little bit more on the question?
Well, basically, where's the next big thing? Like, what's going to enable us to reach the next level? Like, is it some sort of the progress in terms of how we embed domain knowledge in programming languages? Because in my opinion, like based on my experience, I frequently feel like programming languages do not allow me to express the domain very well, because we've actually touched on this a little bit with Sergey, for example, when we were talking about the fact that most of the parallel processing, it depends on some fundamental mathematical properties. Like, for example, you really want to have commutativity if you want to do things out of order, or you need to have associativity if you want to do, for example, something like parallel reduction. And this is critical for big data analysis, but it's also critical for CMD instructions, or just in general parallel processing. So I just wonder if you have had maybe a more positive experience, like maybe you've experienced some way to actually encode this in the programming language, because so far I believe only Guy Steele at some point mentioned that he's working on some research programming language that allows encoding things like associativity, but otherwise I've only used associativity in Agda, for example, but nobody's using Agda. It's not a mainstream language for sure.
So your question here is, it can mean a lot of things in different contexts. So it's, and when you ask it like that, it's really difficult to frame it to give a simple answer. So it's like asking 10 questions at the same time. So let's try to take your question apart and see. So what are the limitations that are caused by compilers in performance, and can they be mitigated? What are the limitations caused by programming languages, and can they be mitigated? What are the limitations caused by the nature of the problems? So you mentioned parallelization. So there's certain problems that are in essence non-parallelizable. So this is their nature. How can this be? How can this be fixed? Also, you have a question of the standard library that you're using. Is it efficient or not? Then you have a question of, if you're building your system from the already pre-made components, how do they work together, and how does everything fit in all together? So there are like 6 or 7 questions. And do you want us to try answering them, because it's a lot of questions?
Well, I was wondering about your personal experience, like each of you, like what do you see as the limiting factor for your work? Like, where do you see the bottleneck? Like, for example, the thing that prevents you from taking full advantage of the APIs or workflows. But basically, what's your bottleneck? Like, what would make your life better if it was true?
Okay, so I can tell you in my work that I make most of the problems with performance are related to the hardware efficiency and a bit surprisingly to the memory subsystem efficiency. So if you're using the object-oriented paradigm and C and C++, so C++, but you can do it in C, and the way the structured data actually influences performance. And now you have the question of, do you want it to be simple or do you want it to be fast? And these are not. If you want it simple, it won't be fast. If you want it fast, it won't be simple. So this is the question for hardware. Every time you process classes, every time you do anything with classes, actually you're hitting the memory wall. And the performance of your CPU doesn't matter that much. You want to buy faster memory. Now, will we be able to fix that? I don't think that will be possible to fix with the object-oriented paradigm such as it is now. I know that the game developers, they use different paradigm, and they're really careful about the memory layouts and how the classes are composed and decomposed and how problem is decomposed, and they focus most on data, not on these abstractions. But I don't see that coming into the mainstream. So I think for some, and probably forever, we'll have a lot of software that's not as fast as we would like. Okay, but for those who are interested in performance, they will be able to obtain what they want with a bit of, with some knowledge and some patience. Yes.
Anyone else would like to share what would they ask for if they had a magic wand?
I think the world really needs some better APIs for parallel computing, and those that not the SPMD ones where you need to learn as a different like kernel language for like that is similar to the way you program GPUs, but some tool that would allow writing seemingly normal code without perhaps even thinking about parallelism that would make the execution of a program parallel. So you know, essentially in the last 20 or even more years, the story of improving hardware is about making it more and more parallel. We sort of around 2004 hit that wall of increasing the frequency of CPUs, and all the recent advances come from different types of parallelizations, from adding multiple cores, for adding more execution units, so that more there can be more concurrency within a single core, and also with SIMD and similar paradigms. But I mean, hardware is there, and there is a clear way to increase parallelism in hardware and make it cheaper and stuff, but software is not there, and it's really painful to program this. Only the world experts can write these kinds of stuff optimally, and many developers are just don't even have the access to these computing environments because they're coding in a higher level language, or even if they're coding in a low level language like C or C++, many are just not aware about these features, and it's not practical to teach everyone these kind of things. So I think we really need to invest like maybe more time and effort into compilers, especially in regard with parallelization, and especially fully automated parallelization. I think this is especially true for for JVM and similar languages that are executed on clients that cannot be properly optimized with native code, and you need to work on their runtimes. So you know, if I had to pick just one direction that really needs lots of more attention, that would be the parallel runtimes, JIT compilers that can exploit all the types of parallelism available in modern CPUs.
Nadav, since you've worked and you're responsible to some extent for the CLang, I wonder what kind of thoughts you have on this support for parallel programming paradigm on a compiler side.
Man, so this is tough because we have, I mentioned earlier, there are only trade-offs in life, and we want to have both safety and observability and high performance, and we want to give our users, our power users, the ability to play with pointers. At the same time, we don't want them to make any mistakes. So this is really tough, and I don't have an answer. And I think that the cases, the domains that were successful were domain-specific languages like CUDA or Python or some technologies that focused on one specific use case. So I don't think that one technology can solve everything, but I agree with the sentiment that we need better programming languages. C++ was designed based on C 40, 50 years ago, evolved over time. It's a very complex language, and our users, this is something, by the way, that I'm seeing every day. People are making mistakes. People pass data structures by value instead of by reference, and that causes a copy, right? People are not aware of the aliasing rules that the compiler has, and compilers can't eliminate loads and stores and generate inefficient code because the language is limiting the compiler. And there are other issues with C++. Yeah, so we need better programming languages. We talked earlier today about Rust. Rust has advantages and disadvantages. Yes, we definitely need better tools. Something that's unrelated to programming languages is the DevOps aspect of these technologies. How do we make profile-guided optimizations, PGO and LTO deployment easier? Because we all know how to do it once, right? We all did build our whatever piece of software with PGO or LTO, but how do you do it at scale? How do you deploy software every day, every commit on a large data center without and supporting all the complexity of multi-versioning and all that? That's a challenge. This is something that Java got right. When you have JIT compilers that trace and record the trace on each individual machine, that totally simplifies the deployment of the technology. This is something that we should improve for C++ and native languages. And then the third thing I mentioned is observability tools. I want to know what's going on within the software. Why are things slow? Right now, it's very difficult. Profilers can tell you where you're spending time, but you don't really know if you're spending time somewhere because of if you're memory bound or if there are some other issues. Yes, you can use performance counters on CPUs, but it's really hard, and you have to work hard to extract these things.
But these are actually very interesting points. And so you mentioned, for example, aliasing. And when I think about aliasing, so even in C++, you cannot have aliasing between different types. Well, technically, you can technically have them, but compiler assumes that you don't do such horrible things. So I guess it, again, somewhat goes back to ability to represent the domain in the code. Because if you are able to do that, like, for example, if you don't use just like, okay, let's use integers for everything, just because I'm too lazy to create a class that wraps an integer. So we don't use strong types. Even in strongly typed languages, we don't use types because, for example, we use strings for pretty much everything. Is it a name? Maybe it's a model or something that is technically an array of characters, but it's not really a string. It's a concept that we do not model. So we just like, oh, let's make it a string.
Well, first of all, with C++, so first of all, characters alias everything. So yes. That's a design decision in C++, and too bad, strings are characters. So now they alias anything. You're dealing with string. You have to reload whatever, the this pointer of the class. You have to reload that because you touched some other memory. Also, something else. With C++, if you have two arguments to a function that are pointers, they may alias one another, which is not something that you have in Rust because of the borrow checker. So that these are two examples of poor aliasing in C++. And of course, when you have these things compound, whenever you have a virtual call or any function call that you can't analyze, that becomes an optimization barrier.
Yeah, but again, it's like if you are able to, like, if you are essentially forced to represent your domain properly, you can avoid aliasing issues. You can also imagine if we had a way to say that, like right now, again, like technically compilers cannot make much assumptions in terms of the data structure layout, just because again, it may be important, maybe it's not important, but oftentimes we just default to using some data layout. Let's say we pick the order of the fields just because that's the order we added them, and not a lot of people think about whether it's important or not, because they assume it's not, but it is. It impacts the memory usage because of the aliasing, and it also impacts the optimizations. For example, if I don't care whether about the layout, maybe a compiler can automatically transform my array of structures into structure of arrays automatically, just because it's not an important thing that I rely on. So that's why I just believe that, like, I don't know, maybe it's just me, but it feels to me that we are missing a way to embed a lot of the knowledge that we have to keep in our heads from like giving it to compilers. So I wonder if maybe, so Sergey mentioned that there are some primitives in compilers that can be used to represent commutativity, associativity, and some other properties. Do it, like, is that the case in CON, for example?
I did not state that for sure. It was just my
that's why I'm asking Nadav, because I'm also not sure. I'm just wondering.
I want to say about the parallelization. That is one thing that I noticed. Parallelization, when I mean parallelization, like running multi-threading. So when you want to run a certain loop on four CPUs or 8 CPUs, whatever. Now there is many compilers support automatic parallelization, multi-threading. So you have a loop and it can generate more or less a parallel version automatically. Now the problem that compilers don't do that is that if the loop is short, then it doesn't pay off, because the runtime is the overhead of creating threads and synchronizing everything is bigger than the actual work.
I mean, I did not mean only a multi-threading kind of parallelism. I also meant like all the other stuff.
Currently, I'm talking about multi-threading because every CPU has multi-threading nowadays. Now the question is, the compiler, there is compiler technology that can generate automatic parallelization of loops, but it never works in practice because small loops have large overhead, and most of the loops in your code are actually small. There are only a handful of them that are actually large, where multi-threading actually pays off. Now, I've never seen
you also need to spend like up to millions of cycles on setting up these threads and stuff. So this is also a concern.
So, but what the idea is really simple. Maybe even to the extent that it's super stupid. It's simple, but there are no tools nowadays that can take the runtime profile of a program. So you can collect a runtime profile with perf or some other tools, and then with the runtime compiler, you feed it using the profile guided optimization. You feed it back to the compiler, and now compiler knows which loops are more important, which are less important. They can actually parallelize the force parallelization of those loops that are large and which have a high enough trip rate. So this is something that probably one or two engineers can implement in 1 month, but nobody has done it. And this would probably make just compiling with these options would make many codes like run 2 or 3 times faster, because most of the software nowadays is still single threaded.
Well, there are many people who are investing in making compiler optimizations aware of profile information and run counts, and I don't know specifically at parallelization. I'm pretty sure.
They're multi-threading.
No, not multi-threading, but vectorization.
Vectorization, yes. But the overhead of vectorization, even if you're wrong, is not that. Even if you make a bad mistake, it's not. It can be 2 times slower, but it cannot be like 200 times slower.
Yes. Yeah. Well, maybe it's one of these things where it's better to let the user have control and just use a pragma.
Yes, but the problem is that most developers don't care, and this would be like you have your continuous integration system. It runs your tests, and then it feeds its data to compiler. You compile again, a compiler compiles, and it does multi-threading on those loops, and voila, you have like 2 or 3 times faster program.
So here's a question. So Java is set up to do this thing, because in Java you have profile available at all time. Do Java virtual machines implement this optimization?
I don't know. I don't know.
Yeah, they also have a very simple, or they have a memory model that allows you to parallelize more easily by avoiding some of the challenges of parallelizing with general C code. So yeah, so I wonder why they haven't. But
well, yeah, I mean, memory model is a complicated topic, especially in C++, and they still like most people who still do not even know the semantics of some of the memory access patterns, like there is the consume thing that nobody understands what it actually means. It's really tough, but I guess the problem, so you mentioned the pragmas, but what I see in practice, like we do have things like, for example, built-in likely. And the problem with these is that even if you are lucky to get it right at some point, it's probably going to become wrong at some other point. So that's why I was wondering, maybe we should have some sort of either interactive environment which continuously pulls the data from the production and tells you that, okay, this is probably wrong. You should probably consider either removing it or maybe changing it. Ideally, obviously, it's going to be all automatic, where you just feed this data from the production all the time. But again, even if you do that, like, what do you do with so there is this problem with profiling, for example, or benchmarking, where you can have a bimodal or some other type of distribution where you have essentially different use cases. And so in one case, for example, let's say the likelihood is true, and in the other case it's always false. And so what are you going to do in the middle? Like, what are you going to do with the average? Average is going to be, I don't know, let's make it true, and then it's going to be bad for one use case but good for a different use case. Like, are there any approaches that can help with these bimodal distributions?
Well, you have LBR, so you have kind of so I guess that it's similar. We can connect that to branch predictors that predict the next branch based on some branch history and other signals, and then in the context of profiling, you have LBR, which kind of lists the last, which is it's a mechanism for tracing or collecting the last sequence of branches, and then some folks at Meta are working on context-sensitive profile-guided optimizations. But in general, we can use compiler techniques for specializing the code for specific paths. If you can duplicate some code and then specialize it for different paths, then this is something that could be beneficial.
Interesting, but how is it going to work, for example, if you have like the root of the tree, because it could be either true or false, or maybe then it follows the same path, it's just the value is going to be different. So how would that work for?
Oh, imagine inlining the same function to 2 call sites. So now you solve the problem, because If you turn your DAG into a tree, then problem solved. Of course, you have a bunch of other problems, but specifically, if you have the problem of, let's say, I'm calling some vector initialization function, and then on one path I'm creating a vector of size 0, and then on another path I'm creating a vector of size 100, and then I need to call malloc. Then yes, you have the diamond problem. But as soon as you inline it into 2 different call sites, then you can solve this problem. But then you have other problems of code bloat and other issues. So yeah, there are many problems and many solutions, and they all have trade-offs. And this is why this domain is so interesting.
And
actually,
what is the...
Actually, on a larger scale, people do this thing where they dynamically try to predict which algorithm is more efficient to solve this specific problem. But people do this in libraries on a larger scales and also in databases. There are, for example, some research databases that tune specific parameters of LSM trees. So, this kind of distributed databases have a trade-off between the speed of reading and the speed of writing to a database. And there are some global parameters that can help you tune this trade-off. And there are some research in dynamically tuning this stuff. So essentially collecting some statistics about the distributions of query, and during runtime fitting these parameters. So you can essentially just dedicate like 1% of the time on some profiling functions. Say you on each query, on each 100th query, you sort of trace what this query does, and then during runtime collect the statistics about this query, and maybe from time to time recompile the whole program in case the distribution of queries changes over time or something like that. So yeah, this is actually used not so widely, but it's picking up adoption.
That's a very interesting idea. It actually reminds me about one of the talks we had a few years ago. It was about picking the data structures based on profiling. So not only we can use PGO-like optimizations to do inlining or some other component optimizations, but we can actually pick an entirely different algorithm or a data structure based on profiling data. So for example, we've noticed that we, let's say, access some data structures in a linear fashion, and actually believe, so one of the things, like, people frequently tell that, oh, linked lists are terrible, and they are, I guess, to some extent at least. But JVM, for example, because it knows that you access them linearly, it can reorder the items in memory such that they are laid out sequentially. Obviously, you still lose some performance for memory indirection because you have to go between these nodes, but at the very least, they are very close. So it's much more likely that you're going to have cache hits because those items will at least fit into maybe L2 or maybe even L1 if you're super lucky. But so I guess you can do a lot based on this profiling data. And but again, unfortunately, it's super, like, I've never seen it being done in smaller companies. I think larger companies like Meta and Google and Microsoft, they do have dedicated teams that can do this at least in some like in some capacity for critical services, but I've never seen it done for maybe smaller services, just because the operational side of things is just way too expensive. So that's super unfortunate. And so I guess so Nadav, now you have a magic wand. One thing, what would you ask for? Just one. You have one wish. I know it's a terrible question. That's why I ask it.
Oof. I don't know. I guess it depends on the problem that we're trying to solve. So there are problems that. Okay, so let me take a step back. I care about compute efficiency because I care about the ecological footprint of our industry. I want the computing industry to be as green as possible and to have a positive impact on the world. One of the areas in which I see the biggest growth in terms of compute needs is machine learning training, and this is something that's worrying to me. And it's also an interesting problem. So this is something that I hope somebody would solve, find better algorithms or be able to make more efficient use of data. So this is definitely one area that if I had a magic wand, I would want the industry to solve that problem and reduce the energy efficiency of training large models.
Which percentage of resources is spent on training models as opposed to inferencing?
I don't know. I can point out to some academic publications. There was a good publication recently about, I think it's called the history of large machine learning models, and it gives a pretty good overview. But I can't. I don't want to speak for any.
I just have a background in deep learning, and I think most of the time is spent on inferencing the models, although these computations are very similar and handled by the same hardware most of the time. So yeah.
And I guess one last thing I'm curious about. So it seems like there is also this problem where, because of the existing hardware we have certain investment on the language side to feed that hardware. So we basically optimize our software to feed the hardware that we have. And because of this, we disincentivize hardware manufacturers to produce hardware that does not fit the languages that we build. And because of this, we end up in this infinite loop of inefficiency where we cannot make our languages better because they are not going to be a good fit for the hardware, and we do not make our hardware better because it's not going to be a good fit for the languages. So do you have some thoughts or ideas or hopes when and if it's going to be resolved?
Yeah. So this reminds me of there's a great paper called the lottery ticket hypothesis, where the hypothesis is that machine learning are dominated by neural networks because we had GPUs available, and GPUs can execute really well, and neural networks can execute really well on GPUs. Had we had better or different architectures, like back in the day, Sun had the Niagara T1 processors that were very sparse. Maybe these would have been better for decision trees. Maybe you would get better algorithms, better outcomes with huge decision trees, the same way we scaled neural networks. Yeah, and we simply found ourselves in the local minimum because of the hardware we had available. So I definitely relate to what you said, where we found ourselves somewhere, so we keep building better hardware for the algorithms that we know that work, but maybe there's a different algorithm somewhere.
Mm-hmm.
Yeah, I don't know.
So yeah, hopefully it's going to be solved at some point, because otherwise it's going to be a bummer. And like I remember, for example, there was a lot of push at some point for hardware transactional memory, and it was even implemented in like Skylakes, and I think it was added initially in Haswell, but it was very buggy. Then it was almost fixed in Skylake. I think it's still buggy. And then I think they completely removed it because they realized they just cannot, like, first of all, it had a lot of limitations because it relied on cache coherence protocols, which are limited. But then they couldn't even make it work just because like it's a pretty complex problem in terms of correctness as well. So we do not get hardware transactional memory, even though funnily enough, GCC has built-in support for this for the transactional APIs. So technically, it's possible even right now to just go and write transactions for regular code instead of concurrency. Most likely, it's not going to be as efficient or fast, but you can.
Which reminds me that. so transactional memory is one example for something that, I mean, if you go out to Twitter and you ask, or Facebook, or to some conference and you ask people to raise their hand if they want transactional memory, some people will say yes.
Yes.
But the thing is, there are trade-offs in engineering, right? And this is a good segue to talking about AVX 512. AVX 512 has a very big footprint on the CPU. You have to increase the size of the register file. You have to increase many of the buses. Programs that don't use AVX 512 become slower. JavaScript and MySQL and a bunch of other stuff become slower because of the introduction of AVX 512. Now, on the spectrum of between GPU and CPUs with 256 wide instructions, is there enough room for AVX 512? Are there really programs that benefit from AVX 512? Yes, I can write one program that it's data parallel enough that it's better than AVX 256, but it's not data parallel, but you also care about latency, so the GPU wouldn't be a better solution. But I don't know. AVX 512 is, I've been very critical of it for years. If you ask cloud vendors what they want, they would probably say higher frequency, more cores. But this feature was added, and I'm not a big fan of it. I don't think that it was the right trade-off. I don't think that making Python and MySQL slower was worth the extra silicon.
Well, good thing that Sergey covered only AVX 256 today.
Yes.
Yeah,
I like
Yeah,
AVX. I like AVX 512. It has some really nice new cool features, like some things that you can vectorize only within that instruction set and not in the regular instruction set. It has these mask registers. These are new.
Sure.
But overall, most people would say something like that. I mean, the features are nice, but the speed up is not that dramatic, and there are also slowdowns. But I guess Sergey is probably the guy who knows most about this.
Yeah, I think I do not agree that there are no applications that there are few applications that can be sped up with AVX 512. I think there are like quite a few. I mean, it was added for a reason, but my biggest concern with it is that it's just so mind-blowingly complex. You just cannot meaningfully program it in all the different ways that these instructions. I mean, they not only added larger vectors that occupy more space and stuff, but they also added a lot more new instructions. And it's really hard to use them efficiently. I mean, people still haven't figured out how to program ARM Neon and AVX2. People are still like finding some very simple improvements that give like 10 to 12 like performance improvements in some basic like string processing algorithms. Yeah, and AVX is just too complex for a human mind. AVX 512, I mean, and this is its main limitation. Also, it's probably just a better path. I mean, if you are going to add some very specific instruction to support some Galois field computations or something, you are better off adding it as a separate hardware module, as a separate chip that does this instruction. I mean, we're living in the years of cloud. We can have a lot of many specialized hardware on the cloud, and that would just communicate with each other to improve the average utilization instead of having a huge part of the chip that is just almost never activated. Yeah.
That's a good point. Yeah.
And that's why we have all these TPUs and other new.
Yeah, every letter of the alphabet has been used to describe these new accelerators: TPUs, XPUs, GPUs, CPUs, and so on.
Yeah, on this optimistic note, I think we can conclude the second day of the Performance Summit. I would like to thank all of our amazing speakers for their time, dedication, and awesome presentations. Again, I've learned a lot. I really appreciate the time. I hope on behalf of our community, I really appreciate your work. Thank you so much. And I hope we'll meet again at some other point to talk about the progress in these interesting areas, performance.
Taras, thank you very much for organizing this.
Thanks,
really-
Sergey. Hope to see you sometimes live next year, maybe live.
Yes, we'll do the live next event. Thank you so much again, and have a wonderful rest of your days.